Good morning, Chem 20s. Our lesson today is on major entities. Really, the purpose of today's lesson is to decide when I take a chemical or a compound or an element and I drop it into water, into a solution, what is going to happen? Let's get started. So, the big question today is why are some compounds soluble in water and others are not? Now, this all comes back to a previous lesson, which is the study of electrolytes. Remember, when a substance actually conducts electricity in an aqueous solution, that is what an electrolyte is. So ideally, an electrolyte is when something breaks down into ions. Now, we're going to start with something that you already know, ionic compounds. So we know that when I take here my crystal lattice of sodium chloride, right, my NaCl, my table salt, it's going to break into its ions. This means that when it breaks into its ions, if I take the conductivity tester and I touch it into the water solution, this salt water solution, it's going to conduct electricity. The light is going to turn on. Well, this is because, again, it breaks up and the water comes along and it pulls the sodium ions away from the chloride ions. And you can see, based on polarity, right, that the negative side of the oxygens in the water lines up to the positive sides of the sodiums and vice versa for the chlorine. This ideally solid ionic compound, when in solution, will break down into ions, hence why it conducts electricity. Now, that is called dissociation. When something dissociates, it separates into ions, and this occurs in an ionic compound. Now, whether it's highly highly soluble ionic or weak soluble ionic, this still dissociates to some extent, meaning the light will turn on. We saw yesterday when we were looking at conductivity that all things will turn that light on. However, something that's highly soluble on the solubility table will turn the light on brighter. Something with low solubility has less ions in the solution. Less of them will break up in water, but the light will still turn on because there are still some ions. Notice in this reaction, when I drop table salt into water or when I drop lithium carbonate into water, I don't need to include water as a reactant. The reason being is because I already know water's present, because when these ions form, aqueous is written in here to let me know that they were dissolved in water. Aqueous, of course, means dissolved in the presence of water. Now, the opposite of an ionic compound would be a molecular compound. And a perfect example of a molecular compound for us would be sucrose. So I've started with a sucrose, let's say a spoon of sugar, solid. I drop it into a bucket of water. Although when you stir it, it looks like it disappears, it doesn't actually break into ions. You'll remember that when we touch the conductivity tester to it, it does not light up. Therefore, there's no ions present. This would be an example of a non-electrolyte. It disappears because it goes from solid sucrose to aqueous sucrose, but at no stage does this molecule ever break down any smaller. It started as a molecule of sucrose, it ends as a molecule of sucrose. All it did was change states by turning into aqueous. Bases, a little quick reminder again, are called ionic hydroxide compounds. These are compounds that are still made up of a cation, anion. The difference is, though, that your anion is a hydroxide. So, like in the example, sodium hydroxide, since it will dissociate into ions, we know from the previous test that it will conduct electricity. So does barium hydroxide, strontium hydroxide. Now, sodium hydroxide is higher solubility, therefore the light will turn on brighter or easier. Barium hydroxide, although it's got low solubility, still a few of these barium hydroxides will dissociate into ions. Therefore, it will conduct electricity. It is considered an electrolyte. Acids are a little trickier, however. Most people assume acids must contain ions because right away they conduct electricity. However, when they start, most acids like HCl isn't an acid at all. HCl gas, that would be molecular, two nonmetals. As soon as though I drop it into water, this neutral substance however, does dissociate, and that's where it gets its acid properties. So that's when it's converted to an ion, and that's when you will notice that the conductivity tester will light up because HCl will dissociate into H positive ions, Cl minus ions. That, of course, means it's an electrolyte because there's ions present, therefore it conducts electricity. In this course, we're going to treat dissociation and ionization very similarly, breaking into ions. The difference is one is ionization is from a neutral atom or molecule converted to ions, and dissociation is not. Now, the key to this whole thing, the trick to everything we're going to do today is the memory aid BioMe. We're going to use this to discuss the rest of the topic. So, when I take a substance, no matter what it is, and I throw it into a bucket of water, we have to make a decision. Does it dissociate into ions, or does it stay together as a molecule like sucrose? Well, BioMe is going to tell us that. So each of these letters actually stand for something. B stands for base, I stands for ionic, A stands for acid, M stands for molecular, and E stands for element. Now you'll notice I put a space between this. This is a made up word, made up words, I guess. What I want to do is I've broken it up into categories. Bia follows a set of rules, and me follows a set of rules. So what I would like to do is let's start with the easiest. Let's start with me. Me represents again moleculars and elements. When either you drop a molecular compound into a bucket of water or an element into a bucket of water, neither of these will ionize or neither of these will dissociate into ions. So under no circumstances do these guys conduct electricity. They will not break up into ions. They will stay together. However, for molecular compounds, we had some memorized molecular compounds. And 6 of these memorized molecular compounds are actually kind of special. And they're special because when I drop them into a bucket of water, they don't stay exactly as they are. Their state, like in the example for sucrose, will actually change into aqueous. And the easiest way, and it's an inappropriate way, but the easiest way to remember which of our memorized molecular compounds actually will change state and turn aqueous when I drop them into water is the phrase, unfortunately, shag me. Sucrose, hydrogen peroxide, ammonia, glucose, methanol, and ethanol, when I drop them into water, they will stay as a molecule, but their state will change in the case of sucrose from solid. The moment it goes into the water, it will now turn to aqueous. This is true for all 6 of these. This is your special cases. So here's what I would like us to do. I'm giving us 3 examples. From these 3 examples, if I was to take each of these individually and throw them into a bucket of water, I would like us to make a list of major entities of what you would find. So let's make sure here I have an appropriate pen. I've got the green I wanted. Perfect. So here's how Mr. Kemp does this. The moment I see gold, I go, ooh, that is an element. So I am in the me category of BioMe. Gold, before I drop it in, is going to be written as AU solid. Therefore, following my rules, molecular and elements never break into ions. So when I drop gold into a bucket of water, I'm going to still have gold solid. And because we're dropping everything into water, of course, we're also going to have water. This is my major entities. This is what I would find in the bucket later on if I was to come back. Ammonia. If I think of ammonia, ammonia is one of my memorized molecular compounds. Because it's memorized, I have to look at the list of shagme. Since ammonia is on the list, I know that first of all, it's memorized, so I can look it up in my table, or you're supposed to know it's NH3 gas. So when I bubble ammonia gas into water, since it's on the shag me list, I know it's going to stay together because everything that's a me stays together. However, it is one of my six special cases, so I know it changes into an aqueous. And of course, don't forget, since I'm putting it into water, water is always present as one of my major entities. Carbon dioxide, again, nonmetal, nonmetal. So this, of course, is also molecular. Since it's molecular, I can go off and I can name this. Carbon dioxide is CO2. Since we breathe it out, we know it's a gas. Now, this is not one of my memorized molecular compounds, therefore I don't have to worry about my special case. It's going to stay exactly as it is. And of course, water is present. So the key to this really is, if you are part of the me, if you're a molecular compound, or if you're an element, you do not break into ions. You stay together. The only time you have to question anything in molecular or elements is if you are under the SHAG-ME list for memorized molecular compounds. There are 6 memorized molecular compounds, and if you are on the list like ammonia, the only thing that changes is once we throw you into a bucket of water, your state turns into aqueous. Okay, this is a perfect spot to stop. When we come back to video 2, we will be looking at BIA, the BIA part of BIOME.